This is Paris Podcast number 66, and today we're talking about bladeless wind turbines. So we've done a whole bunch of podcasts on regular turbines, wind turbines, but these ones are bladeless. And the reason why I wanted to do this is because it is pretty unusual. But once we start going through it, you'll realize how much sense it makes. So to look into bladeless wind turbines, we're going to be looking at a paper called Design and Development of Bladeless Vibration-Based Piezoelectric Energy Harvesting Wind Turbines. And this is open access. You can find it in the link in the description. So typical wind turbines that we know of, you can have like lift-based and drag-based ones, but both of them pretty much rely on having some sort of blades, and these blades go around. However, for bladeless wind turbines, these effectively rely on something called VIV, or vortex-induced vibrations. And this podcast will be split into two parts. The first part will be about its operation, so how these types of wind turbines work, and also some CFD results. The second podcast will be about some experimental results. So let's jump in and talk about how the mechanics of these things, how they work. So first of all, the use of wind energy and the delivery of power for electronic devices via aeroelastic vibration has been studied. Some researchers have focused on collecting aeroelastic energy from airfoils, while others have concentrated on converting energy created by vortex-induced vibrations, so VIV. VIV is an energy harvesting method that uses the vortex shedding phenomena, in which an oscillating lift force is applied to a body and the interaction between the fluid and the solid structure, which in practice is an elastic structure, and that allows engineers to generate electricity. So let's talk about just in plain English what this means. When you have a cylinder or any object that's going up into the sky, you have wind going over it, then you get a von Karman street forming behind it. So the von Karman street is the periodic shedding of vortices from one side to the other. And what that does, it creates changes in the force, the side force. Now, and because of the orientation of this device, this is either lift, or you can kind of think of it, lift and negative lift. So that makes this object bend to the left or bend to the right, depending on when the vortex is being shed. And so it continually vibrates back and forth, and that is called VIV, vortex-induced vibrations. And so this is what they're using to generate electricity. And this is a really great idea because actually one major area of research that's been going on for like 40 or 50 years is how to mitigate vortices from circular structures, from cylinders. And the reason why they wanted to do that is because these forces not only generate noise, but they can also create like the braking to these objects. So these objects can break over time due to the fatigue, or if you get a really high loading, it cyclically loads it and it really reduces its tensile strength, and then that results in premature failure as well. So there's a huge body of research about how to mitigate these vortices, this vortex-induced vibration, and typically it revolves around wrapping a coil around the cylinder. So that's called a helical strake, for example, and this breaks up the coherency of the vortex shedding. But there's actually what this paper shows and this body of work shows is that these vortices can actually be beneficial. So instead of trying to mitigate them for example, chimney stacks or whatever, you can potentially actually use them to generate electricity. So let's continue. A long cylinder mounted on a flexible structure can be used to gather energy created by VIV. The cylinder is susceptible to vortices that regularly shed, causing transverse vibrations. The vibrations can then be transformed into electrical power using piezoelectric generators mounted on the cylinder. Most VIV harvesters have a narrow output band around wind speeds, where the structure's inherent frequency equals the vortex shedding frequency. So what that means is a lot of these VIV wind turbines can't really operate at too wide a range of wind velocities, because in order for these to work, these structures need to vibrate. And when you get to a resonance, so of this object, the resonance frequency, that's when you're going to be getting a lot of vibration, and that's the juicy part. Once you start falling out of the resonance frequency, the vibration drops off dramatically and you don't generate nearly as much energy, as much electricity, I should say. So that means that they're limited to their wind speeds. And this is reminiscent of early blade wind turbines. Like if you go back 20 or 30 years ago, everyone was always going, oh, wind turbines aren't that good because they have such a narrow range of operation. But now they've solved that problem and they can operate over a huge range of wind speeds now, relatively speaking. So it seems to be a very similar problem here, just in earlier days than what the wind turbines are now. So VIV was initially thought to have harmful effects. The viscous effects of a fluid flowing over a cylindrical body, for example, separate from the surface. When this separates, new forces emerge on the surface, which are large enough to cause the structures to vibrate, triggering them to break. This is called aeroelasticity. So while the aeroelastic resonance is considered a nuisance, it provides the technological underpinning of wind energy conversion. Then they talk about another phenomenon called lock-in or synchronization of VIV happens when one of the inherent frequencies of the dynamic design equals the frequency of vortex shedding, resulting in vortex-induced vibrations. So let's talk about lock-in. So lock-in is a fairly fancy term for when you match the vortex shedding frequency to the resonance frequency of the object that you have. Now, what this does is it kind of extends the range that this cylinder will vibrate over in terms of the wind speeds. So once you get into this lock-in range, if you change the wind speeds a little bit, the frequency of this vibration of this structure will still be the same, and it won't fall out of lock-in. So what that means is once you lock in, it's a little bit difficult to break out of this vortex-induced vibration structure stage. Whereas if you don't reach the lock-in stage, if you change the velocity of the wind a little bit, the frequency of the vortex-induced of the vibrations of the structure will change accordingly. So that means that lock-in can be beneficial in terms of really taking advantage of the resonance of this structure. It can also mean that it's very bad because if you have this structure that isn't designed for VIV, then locking in can result in it failing. So it just depends on what you've designed your thing for. So vibrations in wind speed cause the obtained energy levels to drop substantially due to the restricted range of the synchronization region, so this lock-in, which is a severe setback for energy collection. This setback restricts VIV energy harvesting's ability to achieve efficient performance and the intended design. As a result, scientists are working on novel approaches to create broadband energy harvesting systems susceptible to flow-driven vibrations or base harmonic excitations. So in other words, they're trying to look at how can they extend this range of useful operation in terms of wind speeds. The foundation of these solutions is the use of external axial loading or magnetic forces to introduce nonlinear restoration forces. These new nonlinear forces increase power generation by hardening or softening the behavior, resulting in a wide range of resonant frequencies. So what this means is by changing the damping and the stiffness of this structure, you change the resonance frequency, which means that if you change it, you can then extend the range in which you will get resonance over, and you can have this bladeless wind turbine generating electricity at much greater conditions, just by changing the stiffness and the damping. And they're using some fancy electronics and magnetic forces to do this. So, two researchers, Markey and Erturk, analyzed two airfoil-based aeroelastic energy harvesters using piezoelectric transducers and electromagnetic induction. Adding piezoelectric and electromagnetic couplings, they investigated an airfoil with 2 degrees of freedom. So this is interesting that they're using airfoils because obviously airfoils generate lift, so they're actually ideally suited for VIV when you think about it because they generate a lot of side force effectively. But they also have the problem that they can stall very easily if you're not careful. So they have a fairly linear performance up to a certain point, and it gets very nonlinear very quickly. So that's an interesting thing to look at. Then another couple researchers investigated the mechanism of suppressing VIV for circular cylinders by helical wires using the LES turbulence model. So the reason why I'm just reading this is because this goes back to the helical strakes I was talking about, where for years, like people have been looking at how to get rid of this VIV on circular cylinders. Only now for people to come back and go, hey, this is actually beneficial. We can take advantage of this. And these helical wires, these structures going around the cylinders, they're actually very effective at reducing the VIV of cylinders. They can go up to they can cut down their vibrations by 99%. I think in podcast number 2, when I looked at cacti, I've talked about this at length. So if you want to know more about how to suppress VIV on circular cylinders, check out that podcast. But let's continue with this podcast now. So the rigidity of the resonant frequency can be modified by applying magnetic forces to it, increasing the operational life and applicable wind speed range. The energy from the rhythmic movement can be converted into electricity using the electromagnetic induction. And finally, different geometric designs they're looking at to gauge the performance of each and determine the optimal shape that may increase the harvested energy. It's not just the typical circular cross section, but they can look at other cross sections. And actually, in that podcast number 2 with the cacti, we're looking at it's a little bit difficult to explain what the cross section looks like. But if you go back to that podcast, I explain it fairly well. But it's effectively like a circular cross section with like just a jagged edge around it. And that was quite interesting in terms of how effective it was at reducing VIV. Now, in this case, they actually want to increase VIV, at least the range that it operates over. So they're looking at different geometries here. Now, they say when a steady fluid is applied to an elastic bluff body at high enough Reynolds numbers, so Reynolds numbers above 100, they say, the flow breaks from the body surface, resulting in an unsteady broad wake. So in other words, the von Karman street. Now, this is like fluid mechanics 101. One thing that surprised me was that they said a Reynolds number above 100. Now, I know that there's going to be a Reynolds number limit where the von Karman street isn't really going to form that coherently, that well, but I'm not sure what Reynolds number that is. I mean, I've done CFD simulations at like, I think 90, and there was still a really nice von Karman street forming. So I'm not sure why this 100 limit is here. There may be some literature behind it, but I'm not sure. I think it's probably a lot lower than that. If you know what the limiting Reynolds number is for a von Karman street, let me know in the comments below. I'd be interested to know. So 2 unstable shear layers on each side of the body roll up to form vortices, which characterize the flow pattern. This von Karman street. These vortices were produced lead to oscillation, which is then converted to electrical energy through these components, the electromagnetic components. The undisturbed flow speed, U, and the size of the cross-sectional body diameter are connected to the well-known Struhl number. So the Struhl number is a non-dimensional number which characterizes the frequency shedding based on the conditions of the flow and the object that you have in there. And the reason why this is very important is because now you can compare 2 different objects of different sizes and different wind speeds and see what the Struhl numbers are and determine what the frequency sheddings are, which are beneficial for this case. So the frequency of vortex shedding increases as the flow velocity increases from 0, and there is a flow velocity at which the vortex shedding has a frequency close to the body's natural frequency. So the resonance occurs. So significant oscillations can be induced in the body for low mass and mechanical properties. When a body oscillates, it creates a complex interaction with the flow fluid surrounding it, which has 2 unique features. One, a range of flow velocities exists where the vortex shedding frequency is synced with the oscillating frequency, so lock-in, and that results in a very large oscillations. The second feature is that with jumps in oscillation amplitude and the fluid forces acting on the body, the cylinder response may exhibit hysteresis. So hysteresis is where if you increase, if you go to a certain condition from different paths, the resulting condition will be different. So in this case, if you increase the velocity of the wind speed, the frequency shedding might be a certain value at a certain wind speed. But if you drop the wind speed, so you come down from a high wind speed, the frequency shedding might be different. So that's what hysteresis is. So the proposed design incorporated these 2 qualities. However, at low wind speeds, achieving a frequency where the resonance frequency equals the vortex shedding frequency remains a challenge that they're trying to fix. So then they can extend the operating range for these bladeless wind turbines and generate more energy. Everyone loves it. So I just will quickly give the equation for the Struhl number. So Struhl number equals the frequency shedding in hertz times the characteristic length, which for cylinders are usually the cross-sectional diameter, and divided by the free stream velocity. Now, they have a really funky equation for the amount of power harvested from a VIV device. And I'm not going to go through it all, but the power is effectively reliant on the length of the object, the width of it, the thickness, the modulus of elasticity, the second moment of inertia, I think that is. They don't define it, but I'm pretty sure I is what it should be here. second moment of inertia. Then three different electrical properties. There are vibration amplitude, the buoyancy force, that's interesting to me. I didn't see that coming. The mass of floating objects, the beam natural frequency, the supply voltage, the working current, and working temperature. So in other words, everything except the kitchen sink affects how much power you're getting out of this bladeless wind turbine. And who knows, maybe the kitchen sink might affect it as well. So let's look at a few of the designs they've looked at. So the proposed VIV design, they say, while still linked to the bottom, so let's have a quick picture actually. So this is, at the bottom you have a foundation, it's just this cube block. Then on top of that you have a cylinder, a typical cross-sectional cylinder, cylindrical cylinder, mounted on there. And then inside you have all these electrical components that allow this vibration to be converted into electricity. They say the top of the cylinder is unbound, and the amplitude of its oscillation is the largest there. So obviously where it's bound, where it's attached to the ground, it's not going to be oscillating very much there because it's attached to the ground. That's the support. And as you go further away, then you can oscillate more. The structure comprises of polymers reinforced with carbon and or glass fiber, commonly utilized in wind turbine blades. The mast is supported at the top of the rod while the bottom is firmly attached to the ground. It is made of carbon fiber with excellent fatigue resistance and minimal energy leakage when oscillating. Naturally, the design of such a wind turbine is much different from that of a traditional wind turbine. And then they go into some CFD. So they say, based on the experimental results, which showed that at 15 meters per second, the airspeed is where a good amount of energy can be generated. A lower wind speed of 10 meters per second and a higher wind speed of 20 meters per second are also being focused on. So from their experiments that they've done, we'll get into in the next podcast, they found that 15 meters per second is a pretty good range, but they want to look at 10 meters and 20 meters per second as well to see if they can extend this operating range of this bladeless wind turbine. So they go into some results from their CFD, where they have figure 3 shows the vorticity contours for simple cylinders and complex cylinders respectively. Let's talk about the designs that they have. The first one is a simple circular cross-section cylinder. The second one is, it's a cross-sectional cylinder with a circular cross-sectional cylinder, but it has spikes coming out at, let's say if 0 degrees is free stream, at 45 degrees, 135 degrees, what's that, 225 degrees, and 315 degrees. So at the 4 different quadrants. And you would imagine that these cylinders with these spikes coming out would do a good job of breaking up the von Karman street, because it kind of triggers a premature separation. But at certain velocities, the von Karman street does exist. For this particular case, this is only at 10 meters per second. And they say that let's see what it can be noticed that the complex cylindrical shape produces more flow disturbance and intensive vortices. This essentially motivates the mast to vibrate and hence produce more energy. So they say that even at 10 meters per second, which is the lowest speed they looked at, even though the von Karman street is not that coherent for this other wind turbine design, it still produces a lot better vibration. So obviously, the wake is not really a good thing to measure the vibration by in this particular case. It's what's happening very close to the cylinder, and this design worked out quite well. If you look at the regular cylinder, you get a quintessential vortex forming. This is now the vorticity plot, and it's exactly what you see in all the von Karman streets. It's a very coherent one, and yet it didn't didn't produce as much energy as the modified cylinder. In addition to 10 meters per second, they looked at 15 meters per second, and they say that the simulations found that the effects became more evident, that more pressure and more intense vortices are generated at 15 meters per second than 10 meters per second. Hence, more oscillations and more power are generated. So that's to be expected. And then the same thing happens at 20 meters per second, so even more power. Let's have a look at those figures before we go on anymore. So yeah, 15 meters per second, you get the same von Karman street happening for the plain old circular cross-sectional cylinder. For the other cylinder, again, you get a very warped von Karman street forming. Like it's kind of forming now. You get a few vortices, very few coherent shedding vortices happening, but it's still fairly fairly broken up. The pressure and the velocity distributions are not nearly as coherent as for the smooth cylinder, the regular plain old one. And then at 20 meters per second, we'll see that the von Karman street actually starts forming quite nicely now. Even though you have these spikes coming out of the cylinder, the inertial forces are enough to overcome that, and you got a pretty decent von Karman street happening. And that resulted in a lot more oscillation and a lot more energy being extracted. So let's see what they have to say about that part. They say, more pressure contributes to increasing lift forces that are translated as oscillations and more intense vortices, indicating turbulence that causes more vibration in the design and generates more energy. So the CFD results showed that the investigated two factors, geometrical design, shape, and wind speed, play a significant role in creating the oscillations and vibrations that produce more energy. Therefore, it can be concluded that complex cylindrical designs and wind speeds in the range of 15 to 20 meters per second contribute largely to harvesting more energy. So that was the end of their CFD. Now, for the second half of their work, they looked into the experimental side, where they're going to be looking at a whole bunch of different parameters. Hold on, sorry. I got a little bit excited there. But let's finish off this CFD bit. So they say the results show that higher pressure is even created at low wind speeds, producing higher lift forces and more vibrations. The intensity of the vortices at low wind speeds for complex shapes design grows more extensive and even better at wind speeds equal to 15 to 20 meters per second. A considerable amount of power can therefore be harvested for these complex shapes, even at low wind speeds of 5 meters per second, whereas for the smooth circular cross-sectional area cylinders, at 5 meters per second or 10 meters per second, the amount of energy that you can harvest is not nearly as great. So these objects now with different cross-sectional areas are far better at oscillating and producing energy or producing electricity. And again, these complex shapes, even though they don't produce a very coherent von Karman street, they somehow produce a very varied pressure distribution field, and that's what creates the lift force, the side forces in this case. And that's what's important. So that now is the end of the CFD part. We're going to be getting into the experimental part in the next podcast. So that's the end of this podcast. Make sure to like, subscribe. And if you're doing CFD or experiments and you have any validation data that you want to use for your CFD, well, you need to make sure that you have the density of the air you're using measured so you know what to use in your CFD. So to do that, we have the atmosphere hawk as an instrument that accurately measures the temperature, pressure, and humidity. From there, it gives you the density of air very accurately. That gets rid of any of those errors that you'll get that you don't even know about. And a lot of our clients love, or all our clients love it actually. they rave about it. They love it because it's really easy to use. It integrates seamlessly into their current setups, and it's also very accurate. So go on for yourself and make your experiments easier and your CFD validation easier. Link in the description. Peace out, amigos.